Good morning, one and all. Today, we are going to see about the unsymmetrical fault analysis or the unbalanced fault. So, what is unsymmetrical fault? When a network is unsymmetrical fault or loaded, neither the phase current nor the phase voltage will possess the three-phase symmetry. Okay. Say, for example, sometimes due to the fault condition, your phase currents will be changing or due to the fault and the voltage will be changing. And some times the voltage will follow the three-phase symmetry as we have seen in our previous classes. Most of the system faults are unsymmetrical faults. Most of the system faults are unsymmetrical faults because unsymmetrical fault is nothing but your line to ground fault, line to line fault, double line to ground fault, and open conductor faults. So you see the most of the faults occurring, the occurrence of the faults we already seen now. The most of the fault occurring is line to ground fault, around 70% that we have seen. So it consists of unsymmetrical short circuit fault or unsymmetrical faults to the impedance or open conductor faults. If the insulation of the system fails, if the insulation of the system fails sometimes at any point, if the conducting objects comes in a contact with the bare conductor, in unsymmetrical short circuit fault is said to occur. Say, for example, the insulation of the transformer fails. Insulation of the transformer fails. So in that condition also, it will be like line to ground fault because transformer outer part of the transformer will be connected will be connected to the ground. So say for example insulation transformer insulation failures. So that line will touches your that transformer. So that causes a line to ground fault. So immediately the transformer distribution transformer will trip. In the worst case, the distribution transformer immediately it will trip because it's connected to the relay and the circuit breaker. So immediately it will trip. So if the unsymmetrical fault occurs, the unbalanced current will flow in the system. The unbalanced current, the current sometimes in a substation, you'll be feeling in one phase itself, you'll get more current and other two phases will have less current and varying current. So by that time, they can easily analyze some fault happens like that due to this line to ground fault or like that they can easily analyze depends on the current in the each conductor they can easily analyze. So we are using the symmetrical components to analyze the unsymmetrical faults. So even though the fault is unsymmetrical, what we are doing is we are considering the symmetrical component. Already we have seen the symmetrical components in our previous classes. The same thing, we are considering the symmetrical components to analyze this unsymmetrical fault. Next, to determine positive, negative, zero sequence impedance. So we can use Thevenin's theorem or bus impedance matrix. Thevenin's theorem also how to calculate like that. We have seen, and the bus impedance matrix. There are a direct inspection method. Then your bus impedance matrix by using the Z bus building algorithm. That every formulation already we have seen in our previous classes that you please go and see. So here to determine the positive, negative, zero sequence impedance, and thereby what we are doing is we are drawing the like symmetrical analysis components. Like we are drawing this positive sequence, negative sequence networks. We are drawing the positive sequence, negative sequence, and zero sequence networks for the particular fault. So these are the types of the unsymmetrical fault already we have seen. That is line to ground fault, line to line fault, then double line to ground fault, then open conductor fault. Line to ground fault means say for example due to any wind or due to any trees falling onto particular one line and it is touching the ground. So that by line to ground fault. Double line to ground fault means some trees falling on two lines, two phase of the lines and touching the touching each other. Okay, sometimes touching each other in the, and this kind of double line to ground fault is rarely will occur. One line touching the other line. One line touching the other line due to some cut in the wire that it is touching the other line. That is line to line fault. Double line to ground fault, as I said, the trees are falling on to that particular one line and another line. That two lines are touching ground. This line to line fault, sometimes snakes may climb into that particular pole to that particular HV line. So it will get shorted, or some animals like monkeys, or like two lines it will shorter. Sometimes birds sitting on two lines, so it will short that two lines. That also possible. This open conductor fault. Open conductor fault means the conductor gets break, but not touching the ground. Sometimes you will feel line will be, phase will be coming and going like that. So conductor gets open, but it is touching that wire, or there is a break in the wire, full break in the wire, not full break in the wire. There is a small that conductors, because reinforced conductors, no. So even some one conductor also, one small wire also touching that wire. So it is coming and going. The phase is coming and going always. So this kind of things is called open conductor faults. Cause of this unsymmetrical fault, as I said, lightning, due to lightning, lightning in the particular line. Next, wind damage. Wind damage, as I said, the tree falling across the line. Vehicles colliding with the towers or poles. Sometimes you see some tankers, or some lorries will be coming in your streets. That time, what happens is that due to that vehicle height, that two conductors will touch for sometimes. Two conductors will short for sometimes. Immediate tripping will happen, and even though two conductors touching means you'll get say for example two times the current in particular line. So that is a very dangerous situation. Next, as I said, birds shorting lines. Birds might be sitting and shorting the lines, and as I said, monkeys shorting the lines. Next, breaks due to excessive ice loading in like cold countries. Cold countries, what happens is this ice will load in the two conductors. Two conductors, it will touch. That ice will form on to the two conductors, or simply three conductors also. Triple line to ground fault also. Next is snow loading. Snow loading on the particular two conductors. Next is salt spray. Salt spray in the sense sometimes in some like if the conductor is situated near to some oceans or seas, there also salty formation on to the two lines. So there also the possibility of getting short, getting shorter. Okay, and also if that salty spray is frequently there in the particular line. So that is some cases it might be shorting the two conductors. Okay. Some other causes are due to breaking of one or two conductors, or action of fuses and other protective device that may not open the three phases simultaneously. Okay. Breaking of one conductor or two conductor, or action of fuse. Okay. And other protective device that may not open three phase simultaneously. So this three phase fault is rare. Sometimes it might happen also. Next, coming to the short circuit analysis of unbalanced low order systems. So short circuit of unbalanced low order system can be analyzed by the following steps. What are the short circuit analysis? How to make the short circuit analysis of unbalanced system means first you need to draw the positive sequence, negative sequence, and zero sequence networks. First, you need to draw these three networks with appropriate descriptions. We already analyzed like a positive negative sequence, zero sequence network for only fault happens in the like a synchronous machine or synchronous generator or alternator itself. Then for transmission line, how to draw this positive, negative, and zero sequence network. If the fault happens in the particular transmission line. Next, for transformers, how to draw this positive, negative, zero sequence for the transformers if the fault happens. Like that, we already see. For the appropriate description, see, for a transmission line means you need to describe the fault impedance, positive impedance like this. And for transformers, you need to draw the positive sequence, negative sequence, zero sequence like this. For a synchronous machine, what might be the positive sequence, zero sequence, negative sequence? That previous formulation already we have seen in our earlier classes itself. Next, choice of type of faults. Choice of types of faults, that is line to ground, line to line, double line to ground, and location of fault and mathematical description for a particular type of the fault that we need to do. Next, using the Thevenin's theorem or bus impedance matrix, determine the solution of the network equation. Determine the solution of the network equation. In that particular case, fault current, post-fault currents, and pre-fault, post-fault voltages are found at the point of the fault, and all the bus voltage and line flows. Here, as we seen in the previous classes, fault current and the post-fault currents. What is the post-fault current? And fault happens, no? So pre-fault current. After fault, how it will be. So what is the post-fault current? Say for post-fault currents in a particular line, say for example, 1 mega amperes. After fault, how this fault current may change. Post-fault voltages, say for example, 110 kilovolt. After fault happens, what is the voltage found there? Like that, we need to analyze. At that particular thing, we are analyzing at the point of the fault are all bus voltage and the line flows. Next, we are going to analyze the single line to ground fault. Single line to ground fault. In the single line to ground fault, the most common fault that you all know is caused by lightning or by conductors making contact. Conductors making contact with the ground structure. Sometimes lightning happens. Lightning happens to the particular one line. One line suddenly, say for example, that particular spike, it might goes to some like 10,000 volts. 10,000 volts are okay. 10 kilovolts in the particular instance of the time. So what happens means sometimes due to that particular high voltages, sometimes there may be chances of breaking the conductor because the conductor can't withstand that particular voltage or current. So automatically what happens is the conductor may break and touching the ground. So this is also one type of line to ground fault by due to the lightning. So by conductor making contact with the ground structures, as shown in the figure, this is the three-phase generator with the neutral grounding, neutral grounded through the impedance ZN. So here you see this is the phase A, phase B, and phase C. So here the neutral is grounded with the impedance Zn, and the phase A having the impedance of sequence impedance of Zs, and the EMF generated in that particular generator is EA, and having this positive and negative terminal like this. And here the EMF generated in the phase B is EB, having the positive and negative terminal, and EMF generated in the C phase is EC, having positive and negative terminal, and all three like induced EMF having the sequence impedance is Zs as shown in the figure. And the current in the particular A phase is IA, and the current in the B phase is IB, current in the C phase is IC. Here the voltage between this voltage between the C and the ground is BC. Voltage between the B phase and the ground is VB, and the voltage between the A phase and the ground is VA. And here you see the current A phase, we are having the impedance of ZF, fault impedance of ZF, because fault is happening in the particular A phase and touching the ground. So you are having the impedance at the A phase as ZF and having the current as IA in this direction, and also neutral current, having neutral current, it is coming towards in this direction. So this is the single line to ground fault at the phase A, happens at the phase A. It is not mandatory like only it needs to occur at the phase A like that. It may occur in the phase B also. It may occur in the phase C also. For analysis, we have taken as fault is happening in the phase A and touching the ground. That is the neutral or ground. So suppose the line to conductor, line to ground fault occurs on the phase A, connected to the ground through the impedance ZF. So through the impedance ZF, assuming the generator is initially on the no load. So this generator you are assuming on the no load, but practically speaking, there will be a load, because without no load generator, you can't see anywhere here. So here the conductions at the fault bus K are expressed as, so VA, the voltage at the A phase is equal to ZF into IA, and the current at the B phase and C phase is equal to 0. Because why this current at the B phase and C phase is 0 means here the voltage, okay, the voltage due to the fault, the voltage at the particular phase A having the fault current, fault impedance, and as well as some current IA. And here the current, we are assuming the current at B phase and C phase is equal to 0. And fault current IF is nothing but IA, because it is happening in the A phase. Next, symmetrical components of the current. Already we have seen IA not, IA positive and IA negative is equal to 1 by 3 into 1 A squared, 1 A squared A. This is the transformation matrix, and into IA, IB, and IC. This formulation already we have seen in our previous classes itself. If not, you just go back and watch this symmetrical components currents. Next, substitute IB and IC is equal to 0. That is the symmetrical components of current becomes, in the previous formulation, we are substituting IB and IC as 0, because we are assuming that current in the phase B and phase C is 0. So here we are taking the IB as 0 and IC as 0. Next, IA not, IA positive and IA negative is equal to 1 divided by 3 into 1 A squared, 1 A squared, 1 A squared A. Here we are considering the IB component and IC component as 0. And further multiplication of these two matrix, you will become IA not is equal to IA divided by 3, IA positive is equal to IA divided by 3, IA negative is equal to IA divided by 3. So you might have asked one question, why all these three currents are same? Okay, just to multiply it and you find out the same answer only will come. And you just tell in the comment like whether you got the same answer or not. And here, say for example, all three, I am like zero sequence, positive sequence, negative sequence. We are just converting that in terms of the A components. That is current that phase A current component. So IA divided by 3, that is nothing but IF divided by 3. That is IA is nothing but IF, no? So IF by 3. Here IA positive is equal to IA negative is equal to IA not, that is 0 sequence, IA 0 is equal to IA divided by 3. That is nothing but IF divided by 3. From the sequence network of the generator, the symmetrical voltages. So first we have seen the currents. Now we are seeing the, what is the voltages? So voltages VA 0 and VA positive and VA negative is equal to here 0, EA 0, because the voltage at the A phase is 0, the voltage at the this particular B phase, we are converting as EA, and voltage at the negative sequence, voltage at the zero sequence is 0. Voltage at the positive sequence we are taking as EA, and the voltage at the negative sequence we are taking as 0. Here we are taking the impedance as a ZKK 0. That is a Z impedance at the zero sequence impedance, and ZKK positive, that is a positive sequence impedance, and ZKK negative, that is a negative sequence impedance. Rest all elements are 0 here. Next, into IA naught, IA positive, and IA negative. The similar kind of this we already seen in our sequence network of the generator by considering the symmetrical voltage in our previous classes. That is VA is equal to EA minus Z into IA. That is the formulation that we already see. Now we are multiplying this and finding out what is VA naught. So if you multiply this matrix and simplifying it, we'll get the VA naught is equal to minus ZKK naught or ZKK 0, IA 0. That is nothing but minus ZKK 0 into IA positive. That is IA naught is nothing but IA positive. No, so here it is IA positive. Next, VA positive is equal to EA minus ZKK positive into IA positive. Next, VA minus equal to minus ZKK negative into IA negative. That is nothing but minus ZKK negative into IA positive. That is IA negative. We are just rewriting as IA positive. So all terms we are rewriting in terms of IA positive. Here, the phase voltages are given by this symmetrical voltages already we have seen in our previous formulation. VA, VB, VC is equal to 1, 1, 1, 1 A squared A, 1 A squared. This is the transformation matrix into VA naught, VA positive, and VA negative. This is the matrix. Just to multiply this two matrix, you'll get VA is equal to VA 0 and plus VA positive plus VA negative. From this from the condition, VA is equal to ZF into IA. That from the previous formulation, VA is equal to ZF, because the current the phase A only the fault is happening and touching the ground. So it is having the fault impedance ZF. So VA is equal to ZF into IA. So here you see VA naught plus VA positive plus VA negative is equal to ZF into IA, because here you see VA is nothing but VA naught plus VA positive and VA negative. Just we are substituting here. Next step, substitute symmetrical components of the voltage. That is here the symmetrical components of voltage we already calculated. No, these equations we are substituting here. Okay, and reformulating this previous equation. So that is VA naught is equal to minus ZKK naught into IA positive. VA positive is equal to EA minus ZKK positive into IA positive. VA minus equal to minus ZKK minus into IA positive. That we are going to substitute in this equation. Then the equation is reframed like this. Like this, that is nothing but ZF into IA. Now simplifying and taking the common terms outside. So common terms here is IA positive. So EA minus IA positive into this ZKK 0 plus ZKK positive plus ZKK negative. That is equal to ZF into IA. So IA we are written in the terms of IA positive means into 3 into IA positive. So now all we have converted into IA and common impedance terms, because all the zero sequence, positive sequence, and negative sequence, that all terms we are converted into IA positive. That is in terms of positive sequence we converted. So here all IA positive is common here. Now we are taking the IA positive and taking this EA this side. So IA positive into ZKK naught plus ZKK positive plus ZKK negative plus 3 into ZF, okay, equal to EA. That is induced EMF EA. So here by taking this IA positive outside, so IA positive is equal to EA divided by ZKK naught plus ZKK positive plus ZKK negative plus 3 into ZF. This is the positive sequence current, for the line to ground fault, that is fault happening at the particular phase A, that is that A phase is touching the ground wire. So how to calculate this fault current? Fault current IAR, that is nothing but equal to the IF, because how IA is equal to IF already we have seen in our previous formulation. So IF is equal to IA, that is nothing but 3 into IA positive, because IA is nothing but 3 times IA positive, that is equal to 3 into this IA positive. This already we calculate, no? Just you substitute here. So 3 into EA divided by ZKK 0 plus ZKK positive plus ZKK negative plus 3 into ZF. This is the fault current for that particular line to ground fault. That is fault is happening at the particular A phase. On substituting the symmetrical components of the current in the equation, this equation, that is this equation, symmetrical components of current in this equation and this equation, the symmetrical components of voltage and phase voltage at the fault point are obtained. Now we have calculated the fault current. No, similarly, if you substitute all this current components in that particular equation, we can find out the fault voltage, that is VA. We can easily found out. That is VA is equal to ZF into IA. No, so IA, you know, this into ZF. That is nothing but your like fault voltage. Fault voltage is also can be obtained at a particular phase. Next, sequence network from the that voltage equations, from the this equations, that is this two equations, that is IA positive is equal to IA negative, that is equal to IA naught, that is equal to IA divided by 3, that is equal to IF divided by 3, and this equation VA naught, VA positive and VA negative. From these equations, the positive sequence, negative sequence and zero sequence networks are connected in the series as shown in the figure. So what we are doing is here, we are converting that equations into this sequence network format. The same thing for line to ground fault with the impedance Z. So here we are converting the same equations. Say for example, what is VA? VA is equal to, yeah, VA is equal to minus ZKK naught into IA positive. Next, VA positive is equal to EA minus ZKK positive into IA positive. VA minus equal to minus ZKK negative into IA negative. That is nothing but minus ZKK negative into IA positive. Now, with this equation, we are converting simply this voltage equations into our sequence network format. Here you see, yeah. So VA positive is equal to ZKK into EA in the negative, that is minus ZKK plus into EA. Sorry, minus ZKK plus into IA. And also the induced EMF at the particular phase A also you need to mention. So that is there. And the VA negative. So the VA negative is equal to here also I think minus ZKK into IA negative. If you see the equation, yeah, VA negative is equal to minus ZKK negative into IA positive. So that's what here we have written. So VA negative is equal to minus ZKK into IA negative. IA negative minus means it is flowing in this direction. So negative. So here also, if you see the zero sequence components, what is the zero sequence voltage here? VA naught. Yeah, VA naught is equal to minus ZKK into IA positive. Here, VA naught is equal to minus ZKK into IA positive, where ZKK 0 is equal to ZS plus 3 into ZN. This we have already seen ZS plus 3 into Zn. We have seen in our sequence impedance. Just go back through that sequence impedance video. Just watch that particular thing that we already framed this ZKK not equal to ZS plus 3 into Zn. So that also that is the representation here. And here you see the fault impedance is 3 into Zn. 3 into Zn. This is the sequence network for the line to ground fault with the fault impedance. Okay, so here clearly you need to mention the current IA positive, IA negative, and IA 0 also. Here you see mostly ZKK positive is equal to ZKK negative. That is from the previous formulation, the same equation, both ZKK positive is equal to ZKK negative. If the generation is if the generator is or alternator is solidly grounded, that is Zn is equal to 0. And for the voltage fault or direct short circuit fault or solid ground fault, ZF is equal to 0. If the neutral of the generator is ungrounded, then the zero sequence network is open circuit. Zero sequence network is open circuit. That is IA positive is equal to IA negative is equal to IA 0. That is equal to 0. And fault current also 0. If the neutral is ungrounded. If the generator is solidly grounded for the voltage fault, then the impedance of that particular fault impedance is 0, or the neutral impedance also 0. If the generator is solidly grounded. If the neutral of the generator is ungrounded, then the zero sequence network is open circuited. So as we see in our previous formulations. So then this is the case. Next, direct short circuit or voltage fault. Direct short circuit or voltage fault. Here, generator is grounded at the phase A, and also for in the line to ground fault. That is phase A is phase A. The fault is happening. That is fault current is happening in the phase A, but here you see the bolted fault, direct short circuit or bolted fault. This is the figure shown that the direct short circuit, that is line to ground fault, occurs at the phase A as shown in the figure, and having the sequence impedance. All three phases you are having the sequence impedance ZS, and having the current in the phase A as IA, and current in the phase B as IB, and the current in the phase C as IC. This is the direct short circuit line to ground fault at phase A. Now you see the fault impedance ZF. ZF is equal to 0. Okay, because here this is this particular phase only this fault current is happening. So the fault impedance ZF is equal to 0. The conditions of the fault at the bus A are VA is equal to 0, IB is equal to IC is equal to 0, and the fault current is equal to line current, that is IA. Next, the sequence network for the direct short circuit line to ground fault is shown in the figure. This is for the sequence network for the direct short circuit line to ground fault. Here you see this is the VA positive, this is the VA negative, this is the VA 0. And here having the impedance at the VA positive, having the impedance ZKK positive, and here EA, that is induced EMF, you need to mention for positive sequence network, and you're having the positive and negative components mentioned here, and here we are having the current IA negative, and having the impedance ZKK negative, and here IA naught. Here ZKK naught is equal to ZS plus 3 into Zn, as we seen in our previous formulation. Here you see the IA positive is equal to IA negative is equal to IA naught is equal to ZF. Here IF is equal to EA divided by ZKK positive plus ZKK negative plus ZKK naught. Whereas in the previous case, fault impedance is there. Here the fault impedance is not there. Here the fault impedance is not there because sequence network for the direct short circuit fault or for line to ground fault, direct short circuit. So here the no fault impedance is there. That is fault impedance is 0 here. Okay, there is no fault impedance. Whereas in the previous case, you are having the fault impedance as 3 into ZF, I think. So here no fault impedance. So directly the fault current directly it comes like this. Next, pre-fault sequence voltage. Since the fault is assumed to occur when the pre-fault system is under balanced condition, all pre-fault bus voltage contains only for positive sequence components. Okay, only positive sequence components. That is V naught S. V naught S is equal to V1 positive, V1 negative, V1 0 up to VQ positive, VQ negative, and VQ not up to Vn positive, Vn negative, Vn not. So this is all like three phases, like V1 positive up to VQ, next up to Vn. Similarly, this is nothing but this V1 V1 positive, that is voltage 1 positive. Here you are having V1 V10 positive. Here V1 negative will be 0 here. V1 0 sequence also will be 0 here. Similarly, like phase components, VQ positive components only will be having the values, that is VQ not positive, and VQ negative is 0 here, VQ 0 also 0 here, and Vn positive having the voltage of Vn 0 Vn 0 plus, and Vn negative having 0, and Vn 0 also having 0. Because since the fault is assumed to occur when the pre-fault system under the balance condition or pre-fault voltage only contains positive sequence component. So here only positive sequence pre-fault system only under the balance condition, pre-fault system only contains only positive sequence component. So all other negative and 0 sequence components is 0 here. So this is the bus voltage for the pre-fault bus voltage. This is that is mentioned here. Next, what is the post-fault voltage? Positive sequence bus voltages are Vf positive, that is equal to V naught positive plus Zik positive into Zf. That is here you see voltage positive voltage Vf is equal to, that is V naught, that is 0 sequence like positive sequence, sorry, V naught positive sequence plus Zik. So this is the impedance at the particular fault, and also into If. This formulation already you know. Since the fault current is injected at the bus K, so this K is nothing but kth bus. Since the fault current is happening in the bus K, now If is equal to this, all components will become 0. Only this fault positive sequence only will exist. Minus If positive, here also 0, 0. Where Vf positive is equal to V naught positive minus Zik positive into If positive. So the positive sequence post-fault bus voltages are positive sequence post-fault bus voltages are. Previously, we have seen positive sequence current. Here we are seeing positive sequence post-fault bus voltages. So positive sequence pre-fault, sorry, post-fault, after fault bus voltages are Vf1 positive is equal to V naught plus minus Z1K positive into If positive, that is up to kth bus, Vfk positive, that is equal to V naught positive minus Zkk positive into If positive, that is up to Vfn positive, that is equal to V naught positive minus Znk positive into If positive. These are the positive sequence post-fault bus voltages. Next, post-fault negative sequence bus voltage. Similarly, we are framing the post-fault negative sequence bus voltages are Vf 1 negative is equal to minus Z1K negative into IF negative, that is up to VF negative, that is equal to minus ZKK negative into IF negative, that is up to that is kth bus up to nth bus VFN negative is equal to minus ZNK negative into IF negative. Similarly, the post-fault zero sequence bus voltages are the same thing. VF1 0 is equal to minus Z1K naught into IF naught, that is up to VFK naught is equal to minus ZKK naught into IF naught, that is up to VFN naught is equal to minus ZNK naught into IF naught. So sequence line current. What is the sequence line current? Positive sequence line current. Ij positive is equal to VFI positive minus VFJ positive divided by Zij positive. This similar formulation already we have seen previously, because if the positive sequence happening between the bus I and J, okay, that is similarly for negative sequence current between I and J, Ij negative is equal to VFI minus VFI negative sequence minus VFJ negative divided by Zij negative. Then similarly, zero sequence current Ij zero is equal to VFI 0 minus VFJ 0 divided by Zij 0. These are the sequence line current, that is positive sequence current, negative sequence current, and zero sequence currents.